Hey y'all, hope you're having a good day. Today we're just quickly going to go over your study guide and then I'll let y'all study for the rest of the time, or if you have another test or something later today, then I'll see if Coach Reese will let you do that. Yeah, this will be pretty quick because I'm not going to go over the definitions. I'm sure that y'all understand definitions and where to find them. So we'll move on straight to critical thinking. Also, the last problem that I gave you was kind of difficult, and it was kind of unfair for me to give you, I think, now looking back on it, because it was really tough to get the equation that you needed. So that one will not be on your test, but I'll show you the equation that you need and how to solve for that problem. So I'm sorry for that. I didn't realize how detailed and complex it was when I put it in there. So that's my fault. Okay, so let's move quickly then to number 8. And it says, what is the difference between potential and kinetic energy? I've probably said this a million times, so I hope nobody gets it wrong. But potential energy is stored energy. It's not non-existent energy, it's just energy that has the potential to be used in some other form, okay? And then kinetic energy is the energy in motion. So just put that and you'll be fine, okay? And then the standard formula for kinetic energy, what I'm looking for here is the basic one that we went over, where it is kinetic energy equals 1/2 mass times the velocity squared, okay? And that's all I'm looking for that. These should be easy. Give me answers, okay? Also, what is the formula for gravitational potential energy? This one's easy as well. It is UG, gravitational potential energy, equals mass times gravity times height, okay? So UG equals mgh. Okay, that's all I'm looking for there. This one, it was a typo, so if you didn't get it, that is my fault. 11 is, I meant to say, give 3 examples where elastic potential energy might be stored. That was my fault. I wanted to give you a little question on elastic potential energy, and I messed that up. But this will be on your test tomorrow, so make sure you know that 3 examples where elastic potential energy might be stored. So think of like a rubber ball or a rubber band or like a slingshot or a bow and arrow, anything that has like elasticity, okay? So that will be elastic potential energy. That's my fault for that typo there. Okay, this one is a good one to show the to help you understand energy and force, or energy and work, sorry. So it says you use an air hose to exert a constant horizontal force on a puck on a frictionless air table. You keep the hose aimed at the puck so that the force is on the constant as the puck moves a fixed distance. Explain what happens in terms of work and energy. Okay, so work is done on the force by the air, right? So it's making it work, it's making it go, okay? And then also the puck is going to gain a certain type of energy because it's moving. And I hope that you know that that certain type of energy would be kinetic energy, because that's energy of motion, okay? Okay, the difference between an elastic and an inelastic collision. So I want you to tell me in terms of kinetic energy. So kinetic energy does not change in an elastic collision. That's what I want you to put down, okay? It does not change. In an inelastic collision, kinetic energy is decreases, okay? It really would just change forms, okay? But the kinetic energy decreases because we know with the law of conservation of energy, it's not destroyed. It just changed forms. But an inelastic collision, the kinetic energy decreases, okay? Okay, number 14 has to do with time and velocity. So I hope it wasn't too confusing, but I'll explain it to you. Okay, 14 says, a ball drops 20 meters. When it has fallen half the distance, or 10 meters, half of its energy is potential and half is kinetic. when the ball has fallen instead for half the amount of time it takes to fall, will more, less, or exactly half of its energy be potential energy? Okay, so what you need to know here is that when something falls, the velocity increases, right? So if it's only fallen for half the amount of time it takes to fall, it's not going to have fallen half the distance, right? Because it's less velocity at the top. So that means it hasn't even fallen halfway. So you would have more potential energy than you would kinetic energy because it hasn't reached that middle point yet, because velocity increases as it falls. Okay, so this is a difference in distance and time and velocity. Okay, so make sure you know that. Okay, so this is a simple one as well. So 15 says, explain how work and a change in the form of energy are related. Okay, so basically all you need to know is that work is the transfer of energy. Okay, that's when you have to do with the puck, like the puck moves from potential to kinetic energy. Okay, so that is how work and energy are really related. Okay, all right, let's look at the problem solving. Some of these are pretty simple. I just wanted to make sure you knew the basic understandings. Okay, this says a 1,600 kilogram car travels at a speed of 12.5 meters per second. What is its kinetic energy? All right, this one we're just going to use our basic kinetic energy formula, okay? So we've got K equals 1/2 mass times velocity squared. All right, we are given our mass, 1,600 kilograms. We're also given our velocity, 12.5. All right, and we just square that velocity. I feel like that could be the biggest mistake. Don't forget that. You square the velocity. And we end up getting 1.3 times 10 to the third joules. Ten to the fifth joules, sorry. Knew I was looking at the wrong one. Times 10 to the fifth. Okay, so you just use your simple equation right here. Just use your simple kinetic energy equation. Okay, good. All right. The next one hang on just a second, let me erase. Okay, the next one says, how much potential energy does Tim with a mass of 60 kilograms gain when he climbs a gymnasium rope a distance of 3.5 meters? Sorry. All right, so here we're just going to use UG equals MGH. All right. So we have our mass, 60. We have our gravity is 9.8. And we have our height is 3.5 meters. All right, and that gives us 2.1 times 10 to the third joules. Okay, so you just use your gravitational potential energy formula there. And I want to make sure, I think I might have given you the wrong answer on the previous problem. I was looking at my work wrong. For 16, I can't remember what I gave you, but it's 1.3 times 10 to the 5th joules. Okay. I was looking at this problem, I think, but it's, again, number 16 for kinetic energy is 1.3 times 10 to the 5th joules. Okay, you still do it the same way that I showed you. I just think I wrote down the wrong answer from my work in here. Sorry. All right, let's look at 18. 18 has to do with remembering that potential and kinetic energy kind of like are opposites, but proportional. Okay, so it says a large chunk of ice with a mass of 20 kilograms falls from a roof 8 meters above the ground. Find the kinetic energy of the ice when it reaches the ground. Okay, so here we're looking for K2. But we need to remember that when we have K1 plus UG1 plus UG1 is equal to K2 plus UG2. Okay, we need to remember though that our K1 when we start is going to be 0. It's all potential energy. So we need to find our gravitational potential energy of the initial, and that will give us our kinetic energy. Okay, because then these will be equivalent because UG2 will be 0 at the end. Okay, so we just need to find our UGI right there. And that'll give us our K2, okay? Because they'll be equivalent. Okay, so to find our UGI, we just have to use MGH, okay? And that means we've got our mass is 20, gravity is 9.8, and the height is 8 meters. All right, and that gives us 1.6 times 10 to the 3rd joules. And so since we found the UGI, that ends up giving us our kinetic energy when it reaches the ground, so our K2. So our UGI is 1.6 times 10 to the 3rd joules, so our kinetic energy of the ice when it reaches the ground must be 1.6 times 10 to the 3rd joules as well. Okay, good. Okay. Number 19 says, looking at the previous problem, what is the speed of the ice when it reaches the ground? Okay, so now we're looking for V2. All right, so our K2, what we just found, is equal to 1/2 times the mass times V2 squared. Okay, so all we have to do now is get V2 on a side by itself, and when we do that, we get V2 equals the square root of 2 times the final kinetic energy over m. This is very close to one of your practice problems, okay? So this is the formula we're going to use. Okay, now you just have to plug in. So we found our K2 earlier. So I did clean this board today. It just gets so dirty so quickly. Sprayed on myself. Okay, so when we plug it in, we get V2 equals the square root of 2 times 1.6 times 10 to the third, that's the K2 that we just found, divided by our mass, which we've had from the beginning, is 20. Okay, and we get 12.65, and it's meters per second, because we are looking for the velocity. So all I did there was plug in. Okay. Good. I don't think I'm going to show you this last one because I don't want it to confuse you for the test tomorrow, because I'm not going to put it on the test because it's kind of irrelevant now looking back on it from what we've learned so far. So I won't confuse you with that anymore. But yeah, so if y'all have any questions, just get Coach Reese to send them to me, and I will make sure I check them. I get off work at 3 on Thursday, so sorry it's Wednesday right now here, but you'll get this on Thursday. But yeah, so I'll be off at 3 on Thursday, so I'll be able to check his messages if you have any questions then. But yeah, I hope this wasn't too difficult. Like I said, don't worry about number 20. Just make sure you know concepts, know how work and energy are related, know the law of conservation of energy, know your definitions and just your formulas so you can see how the speed or something might be affected if you increase mass or decrease mass, or does it have anything to do with the mass, or things like that. Okay, so just, yeah, take the time to study for this. You guys are in the home stretch and you'll be off to college before you know it. I'm super proud of y'all, and yeah, good luck on your test on Friday, and yeah, I'll talk to you soon. Bye.